Physics lost a bright star last week when Stephen Hawking, world-renowned cosmologist, theoretical physicist, and science communicator, died at the age of 76. Although he was just given a few years to live when first diagnosed with motor-neurone disease in 1963, aged just 21, and at the beginning of his graduate studies in Cambridge, he defied medical predictions and lived for another 50 years. Somehow it still doesn't feel like it was long enough, but few can say they've made such good use of their time. I hadn't planned this episode, of course, so I apologise if I miss anything out, but I wanted to pay tribute. Well, it's more like I had to. It would be remiss of me not to talk about Stephen Hawking. Not just because of his contributions to physics, the inspirational life that he led, and the fact that amongst his studies in cosmology, he also advocated a lot about the field of existential risk studies that's been the focus of most of this podcast so far, but also because of the sheer magnitude of his presence on the world stage as a physicist. In a recent survey where adult Americans were asked to name one living scientist, 43% of people named Stephen Hawking. Those were the ones that could name a scientist. The next person on the list was Neil deGrasse Tyson with 6%. This is the gulf, at least in terms of the popular understanding of science, between Stephen and the competition. And I think it's here that we're really going to miss him. So let's talk about his life and his scientific legacy. In physics, he's best remembered for his contributions to cosmology, especially in considering the physics of singularities and black holes. We haven't really given a full account of black holes or cosmology just yet, and hopefully in the fullness of time we will, but I'll try to explain them just enough to get on to what Hawking discovered. So black holes. These are regions of space and time where the gravitational field is so strong that nothing, not even light, can escape. And they've been theorised since the early 20th century. They're one of the simplest permissible solutions to Einstein's general relativity field equations. Schwarzschild, the scientist, found this mathematical solution in 1916, the year after Einstein first published his field equations that described the nature of gravity. But it took another 40 years until 1958 for a more modern interpretation of what this mathematical solution might mean in our real physical world. A black hole. General relativity gives us a set of equations that describe in incredible detail how gravity works on large scales. And we knew that it was accurate because it explains everything that we already knew to be true and more. Like special relativity, it reduces down to the equations that we know already for most situations. In this case, if the mass is small enough, the general relativity equations look like Newton's gravity, and all is well. We get the physics that we're familiar with. But we know that it's true, or maybe more complete as a theory, because it describes some things that Newton's gravity doesn't. Famously, it predicts that light should be deflected by gravitational fields, and this was tested in a famous expedition that proved Einstein right, where, during a solar eclipse, scientists including Arthur Eddington observed that light from the background stars was deflected by the sun. It had to pass by the gravitational field of the sun, and that deflected it by the precise amount that was predicted by general relativity. But just because the equations were a better description of gravity and they had certain solutions, it didn't necessarily mean that the objects represented by those solutions actually had to exist somewhere out there in the universe. So it took a long time for people to observe actual astrophysical objects out there in space and realise that they were looking at this particular black hole solution to the equations. I think this should give you a real sense of how amazing it is that we have theories like general relativity they're mathematical ways of describing the universe, and they can predict things about phenomena that we've never even seen before. That to me is wild. This is how Hawking explained black holes in 2008 in a public lecture with a well-known analogy. He said, quote, "In 1915, Einstein put forward his revolutionary general theory of relativity. In this, space and time were no longer separate and independent entities. Instead, they were just different directions in a single object called space-time. This space-time was not flat, but was warped and curved by the matter and energy in it. In order to understand this, consider a sheet of rubber with a weight placed on it, to represent a star. The weight will form a depression in the rubber, and will cause the sheet near the star to be curved rather than flat. If one now rolls marbles on the rubber sheet, their paths will be curved rather than being straight lines. Consider now placing heavier and heavier and more concentrated weights on the rubber sheet. They will depress the sheet more and more, distorting the orbits of particles around the sheet more and more. Eventually, at a critical weight and size, they will make a bottomless hole in the sheet that particles can fall into, but nothing can get out of. End quote. A black hole is a finite region of space. The Schwarzschild radius, the size of the black hole, can be calculated by the fairly simple formula R equals 2gm over c squared. The region of spacetime inside this radius, perhaps infinitely warped in a sense, was considered one of the most mysterious places in the universe. Potentially, since nothing, not even light, can escape the event horizon, the contents were unknowable. There's simply no way of pulling that information back out. Hawking's first breakthrough, working with the mathematician Roger Penrose, was to demonstrate that there may be singularities at the heart of black holes. That is to say, a singularity is a region, a point in space-time, where the curvature due to gravity is infinite. That's a time-like singularity. Or else a region where some finite amount of matter is compressed to a single point. A space-like singularity, or a point of infinite density. Now, it's so mind-bendingly difficult to imagine what a singularity might look like. I mean, this infinite point of gravitation, of density, of curvature. It's probably a good thing that in most theories, any such singularity, if it did exist, would be cloaked in a black hole. This prevents us from seeing this impossible, but according to Hawking, inevitable region of spacetime, where things are infinitely dense and the laws break down. Because nature is concealing this for modesty's sake, the idea that you can't ever see a naked singularity is called the cosmic censorship hypothesis. Hawking's original theory suggested an intimate link between singularities and cosmology, the evolution of the universe as a whole. He suggested in his PhD thesis that the universe may have begun as a singularity. In fact, his interpretation of general relativity seemed to show him that time had a beginning, and that the universe did begin in a singularity. In many ways, this makes sense as a consequence from the theory of a universe that does expand. If you accept the theory that the universe is expanding, and expanding endlessly, what happens when you run the film in reverse? Well, then you'd expect it to contract down, smaller and smaller, to a volume so tiny that it's eventually a point. But then, where did all the matter and energy in the universe come from? There must have been a finite amount of energy, which must be conserved, concentrated at an infinitely small point, a singularity. Now, it turns out that while this idea makes a lot of intuitive sense, it doesn't quite work in our current models of cosmology. This is because of something called cosmological inflationary theory, which basically states that you can't do this nice simple extrapolation backwards to find a singularity at the beginning of time. More in the cosmology episodes when we get there. Hawking later decided, and mentioned in A Brief History of Time, that the idea of the universe beginning with a singularity was contradicted by quantum mechanics, so he no longer believed that that was the case. It was this intimate link between black holes and cosmology that is perhaps the hallmark of Hawking's work. In realising that the mathematics of general relativity and the evolution of a singularity could be applied as a model for the universe, only in reverse, Hawking and Penrose obtained profound insights into our cosmological history. When Hawking's career began, there was still considerable debate over whether the universe was expanding, contracting, or steady state. Einstein, whose theory had implied the possibility of a universe that changed in time, was uncomfortable with the implication that gravity should cause the universe to collapse. So much so that he added his famous cosmological constant to balance out the collapsing influence of gravity, so that the universe could be steady state. This argument between the steady state people and the people who thought that the universe was expanding is a physics argument with really deep philosophical consequences, like so much of what Stephen studied. We knew by this time that galaxies appeared to be flying apart from each other. The wavelength of light from distant galaxies is stretched. You know when a car zooms away from you? Meow. It's lower in pitch when it's moving away from you, and higher in pitch when it's moving towards you. Well, that's exactly the Doppler effect that stretches the wavelength of light from distant galaxies, and tells us that they're flying apart from us. For the steady-state theorists, then, the idea that these galaxies are constantly flying apart is a bit of a problem, because they also believe in cosmological principles like the idea that the universe should always look the same no matter what direction you look in. If the universe is to be a steady state, then it has to remain looking the same through all of time as well. For the steady-state theorists, then, you imagine the universe, space-time, as sort of eternally present. So, in order for this to work with galaxies flying apart, as the galaxies fly apart from each other, you need new ones to be formed by matter that's popping into existence throughout space. The universe exists forever and always looks the same, regardless of what direction you look in or where you are in the universe, because new galaxies form to fill the spots of old ones. Of course, this was already in trouble with observations by the time of Hawking, but he was one of the people who mathematically proved that it wasn't the case. And of course, this is philosophically important. If the universe is eternal and doesn't care about time, you can dispense with a rather tricky set of questions. What existed before the universe? How did time begin? Why did time begin? You can just say that it's always been so. There's no sense thinking about a start to time, a beginning of the universe, just events that happened before now. But the expansionary theory is totally different. The universe cares now about the passing of time. There is some date, we think around 14 billion years ago, when the universe actually began. And since it's a dynamic, evolving object, it has an ultimate fate too, which isn't just go on looking the same forever. In fact, it's a theory with incredibly profound consequences. In that steady-state model, things can go on forever, life can go on forever. In our current model, it cannot. Eventually, energy dissipates across the infinitely expanding wastes of space and time, and nothing can exist. This too gels with our intuition, but it's sad as well. Since it seems that the universe does care about the arrow of time, and which way it's pointing, and evolves towards this cold and dismal soup, interesting things like stars and people and black holes aren't everlasting. Instead, we're a spark that glows for a little while and then cools and fades away. That's where we are now. By Hawking's day, it was generally accepted that the universe was expanding, but debate remained about how to reconcile theory with observation. And people were coming in with all kinds of different theories, many of them motivated by philosophy as well as physics. The Pope, for example, liked the Big Bang Theory because he felt like it sounded a lot like Genesis 1. There's a flash of light and the Earth is created, the universe is created in that way. Meanwhile, there were some Russian physicists who were coming up with an idea that the universe was collapsing and then re-expanding, and then collapsing and re-expanding again. That once it got to a certain point of density, general relativity predicted that it would burst back out again. And this was good for their philosophical point of view as well, because then they didn't have to deal with this thorny question of a universe that began, which for some people implies a creator. If that was the case, then they could have their very Marxist theory where everything is completely deterministic, and the universe just collapses and rebounds over and over again, and they don't need to worry about the beginning of the universe. But what Hawking and Penrose demonstrated mathematically in Hawking's PhD thesis is that that theory couldn't quite work, that singularities would in fact exist in general relativity. They mathematically demonstrated that there would be these points in the universe where the laws of physics as we know them cannot be applied. Here's Hawking again in a public lecture discussing the consequence of his singularity theorems for cosmology. He said, quote, "Although the singularity theorems of Penrose and myself predicted that the universe had a beginning, they didn't say how it had begun. The equations of general relativity would break down at the singularity. Thus Einstein's theory cannot possibly predict how the universe will begin, but only how it will evolve once it has begun." There are two attitudes one can take to the results of Penrose and myself. One is that God chose how the universe began for reasons that we could not understand. This was how Pope John Paul felt. At a conference on cosmology in the Vatican, the Pope told the delegates that it was okay to study the universe after it began, but they should not inquire into the beginning itself, because that was the moment of creation, and the work of God. I didn't fancy the thought of being handed over to the Inquisition like Galileo. I was glad that he didn't realise that I'd presented a paper at the conference suggesting how the universe began. The other interpretation of our results, which is favoured by most scientists, is that it indicates that the general theory of relativity breaks down in the very strong gravitational fields in the early universe. It has to be replaced by a more complete theory. One would expect this anyway, because general relativity does not take account of the small-scale structure of matter, which is governed by quantum theory. This does not matter normally, because the scale of the universe is enormous compared to the microscopic scales of quantum theory. But when the universe is Planck size, a billion trillion trillionth of a centimetre, the two scales are the same, and quantum theory has to be taken into account." End quote. For matter on the scale of that singularity, quantum mechanical effects should become important and dominate. Clearly, surrounding a region of infinite density, you're going to need to take into account of the gravitational effects and general relativity. But famously, the great unsolved problem of theoretical physics in the last century is finding a theory that unifies general relativity and quantum mechanics. This theory would explain how the universe behaves inside black holes, and also perhaps at the very dawn of time itself. It is this effort to which Hawking would devote much of his later career, and despite numerous candidates like loop quantum gravity, string theory, and M-theory being proposed by a whole range of scientists that could solve the problem, none has yet been fully accepted by the scientific community. Hawking would continue for the rest of his career to look at the potential for finding this ultimate theory, the theory of everything, through analysis of black holes. After all, they were regions of space where the two apparently contradictory theories ran headlong into each other, the perfect place to look for such contradictions, and perhaps the answers to how they could be unified. His next great breakthrough came in 1974. He had attempted to apply the laws of thermodynamics and energy conservation to black holes. They held everywhere else, so why not here? In doing so, in collaboration with others, he discovered that even black holes were not a steady-state solution for matter in the universe. They must gradually emit radiation and evaporate. The average black hole is so cold that this radiation is unlikely to be experimentally visible, at least not from the black holes we've discovered, where it's swamped by radiation from the surrounding infalling material. As that stuff spirals around a black hole, it tends to emit light that just drowns out any signal from the Hawking radiation. Now, the mechanism by which this Hawking radiation is released is complicated. It's generally described by saying that, close to the event horizon, particle-antiparticle pairs are continuously formed. One half of them spirals into the black hole, while the other half is freed and emitted as radiation. In an alternative description, particle-antiparticle pairs form just inside the black hole, but one of them can escape due to quantum tunneling, which means there's a certain uncertainty about precise positions of matter, and quantum tunneling as a phenomenon means that sometimes impossible things can happen in quantum mechanics, essentially. Particles can escape from energy wells that they shouldn't have the energy to due to this uncertainty. Although a black hole of just the mass of the Sun will live for 10 to the 73 years, 10 with 73 zeros after it, the fact that they do gradually shrink and evaporate does have profound consequences for the long-term fate of the universe. Hawking radiation was probably Hawking's greatest discovery. He had found a link between the general relativity that discovered the behaviour of black holes and the quantum mechanical uncertainty that led to the radiation. Here was, perhaps, more evidence that black holes could not only help us understand cosmology, as well as being fascinating objects by themselves, but maybe also lead towards a theory of quantum gravity, a theory of everything. But it also presented a great problem for physicists: the information paradox. Quantum mechanics is famously incredibly confusing, and we haven't got around to explaining it fully yet, so I'll give you the quick notes of how it shows up here. In quantum mechanics, we change our view of the universe almost completely. In a classical universe, we think about particles like billiard balls that float around and bash into each other, and everything is completely predictable, because if you know where all the billiard balls are at time A, and how fast they're moving, then you can predict how they'll collide with each other, you can work out where they'll go next. The universe is fully determined by the previous state that it was in. Does that make sense? Good, because it's about to get complicated. In quantum mechanics, instead of having these particles with defined positions and momentums, they're replaced with wave functions. Maybe you've heard of Schrödinger's cat. Until we open the box, we can't know if the cat is alive or dead. Therefore, while the box is closed, the cat, in some sense, is both dead and alive. So, in the cat analogy, the wave function is like a probability distribution. It tells you how likely you are to find an alive cat or a dead cat when you open the box. The act of measuring something is opening the box, and we say that it collapses the wave function. Before you collapse the wave function, there's a whole range of possibilities for the system. But once you measure, you collapse it, and the system is forced into one possibility. The wave function of the cat in the box, then, before we take the measurement, is a superposition, a sum of two wave functions, one of a living cat and one of a dead cat. And the uncertainty principle tells us that similar things apply to physical systems. In other words, the most complete possible description you can give of a particle isn't saying, it's over here, it's in position X with speed Y and energy Z, and so on. These things are only true after you make the measurement and collapse the wave function to give the values good defined values. The most complete description you can give of a system is its wave function, which assigns probabilities to all of the possible states it can take, all of the possible outcomes of a measurement. So now we have a new kind of determinism, or do we? A way of determining future events according to past events. Instead of saying the particle is moving in this direction at this speed, so in 5 minutes it'll definitely be here, we now say the particle's wave function contains information about that particle, and that information is being continuously updated, scrambled as the particle moves through time, space, electromagnetic fields, whatever. So when I take a measurement, I'll collapse that wave function, I'll force the particle to exist in a particular place. So I may never retrieve all of the information that was in the wave function before and afterwards, but it still exists. There's no point where that information doesn't exist. It's just being scrambled and evolving. And there's no physical phenomenon that can destroy that information about a particle. I hope that makes just a little bit of sense. It baffles me, and hopefully I'll be able to explain it better at some point. But the key idea is that quantum information is in a sense conserved, even if it can be scrambled beyond all repair or retrieval. In a perfectly classical deterministic universe, you can always just run the clock backwards. You can specify where things are at time B, run the clock backwards to time A, and watch as all the billiard balls go back on their previous trajectories. You can reverse time and get back to where you started from. In quantum mechanics, this becomes harder to argue because it seems like when you make measurements, you could measure it in being in different situations at the same time. But there should at least be some property, the information stored in the wave function, that's changing smoothly and continuously, even if we can never observe the full range of that data when we take measurements. Got it? Phew. Don't worry if not, because we're going to do so many shows about this someday and get it righter than we have now. So why are black holes a problem for quantum information? Well, the black holes are absorbing quantum information. The particles are falling into them, and we can't ever see them again. So we can never measure any of the information about the wave functions of those particles. That's fine though, because the information is still there. The particle's information, wherever it is, presumably still exists. It just might be behind the event horizon, where we can't access it. But there's no law against that. Except Hawking now tells us that the black hole is gradually evaporating as it releases Hawking radiation. Eventually, even if it takes trillions upon trillions of years, it will vanish completely. So when it vanishes, what happens to the information? Is it conserved, or is our theory wrong? As with many points in physics, especially where it bleeds into philosophy like this, part of you might be saying, oh, does it really matter if quantum information is lost under these abstract circumstances? Maybe if you're a particle or a wave function that's falling into a black hole, that your information will permanently be destroyed will upset you a little bit. Maybe then you'd care. But energy and matter and stuff is conserved by Hawking radiation. Hawking radiation allows black holes to evaporate without destroying energy. The black hole evaporation doesn't ruin these things, and they're probably more important for the laws of physics to make sense. But Hawking himself certainly didn't see it that way. He points out that if information is lost anywhere, it means that the determinism breaks down. We can't be sure that past events cause one set of future events. If black holes can scramble the order of the universe and just emit anything, it makes the future impossible to predict, even in principle, even if you knew the wave functions. And once a law is no longer universal, it's not a law. So if you can prove that the condition doesn't hold somewhere, who's to say it's not being violated in all kinds of ways? Hawking was, for a very long time, convinced that information truly was lost in black holes, with all the profound consequences that has. Obviously, it's a problem that defies easy experimental testing, since Hawking radiation is really, really, really hard to see. It became the subject of one of his famous scientific bets with Kip Thorne. But in the 1990s, he conceded that he was wrong, and that information may well be conserved in black holes, even if it is scrambled beyond all recognition. The resolution to the paradox that caused Hawking to concede the bet was something called black hole complementarity. The idea here is that all of the physics that occurs on the interior of a black hole is mirrored and can be described by phenomena that occur just outside of the black hole. So if you're an observer living in a black hole and you somehow survived, you can see the information inside. If you're on the outside, you see the information remaining just outside the black hole, being scrambled, and then being re-radiated back into space as Hawking radiation. For both sets of observers, information is conserved, and the laws of physics, or at least this one, can hold. Voila, no paradox. Explaining why the phenomenon on the outside of a black hole mirror the phenomenon in the interior requires some complicated mathematics and quantum field theory, which I freely admit I don't understand. But in some ways I might not have to, because this is not the end of the information paradox story. It was discovered quite a few years ago in 2012 that this model doesn't quite work. It turns out that if you do the maths and follow through the evaporation of a black hole to the end, at some point the information on the outside is not balanced with the information on the inside. The theory contradicts itself and doesn't preserve what you want it to, so now there's a new paradox that needs to be resolved. And in fact, the scientists who discovered this contradiction posed a very controversial resolution, a black hole firewall that would break bonds of quantum entanglement between particles, releasing colossal amounts of energy just inside the event horizon. But this couldn't possibly be explained by general relativity as it is at the moment, even if it did exist. Okay, we're getting a little bit beyond what this tribute episode can possibly handle. The main message here is that, although for a while we thought the paradox was solved, at the moment it's back and worse than ever. And unless it can be resolved, some pretty major physicsy ideas will have to change. If anyone would like an episode that tries to explain just this, I'll try and get one out for you. More than 40 years after Hawking's seminal paper in 1974 that introduced Hawking radiation, the paradox is still a problem. And he was still coming up with conceptual solutions to the paradox as late as 2016. Of course, Hawking was not always right. Another bet that he did lose in the end was betting that the Higgs boson would never be discovered. When it was in 2013, he immediately conceded and opined that Higgs should be awarded the Nobel Prize, which he was. He also had an immense sense of humour. Particularly delightful to me as a Monty Python fan was when he sang the Galaxy song. You should look that up as soon as you're done with me. His book, A Brief History of Time, released in 1988, became a bestseller, introducing more than 10 million readers to concepts in fundamental physics, including some that Hawking discovered himself. Amongst his academic achievements, the litany is too long to list, to be honest, he became Lucasian Professor of Mathematics at Cambridge, and so followed in the footsteps of Isaac Newton and Paul Dirac as some of the greatest English physicists. In his later years, as one of the most iconic physicists and communicators of science ever to have lived, Hawking brought the ideas of fundamental physics to a wide audience. He spoke eloquently on issues such as the treatment of people with disabilities and the National Health Service. With particular relevance to the Teotwalki specials, towards the end of his life, Hawking was focused on the philosophical issues surrounding the long-term future of humanity. Hawking regularly used his prominent position as a theoretical physicist to talk about other issues, such as existential risks. He said to the BBC in 2016, quote, "Although the chance of a disaster to planet Earth in a given year may be quite low, it adds up over time and becomes a near certainty in the next 1,000 or 10,000 years. We will not establish self-sustaining colonies in space for at least the next 100 years, so we have to be very careful in this period." End quote. And kind of echoes some of the stuff we've been saying. He warned about the dangers from artificial intelligence and climate change tipping points, both of which we've discussed in this existential risks series. He warned about the threats from aliens too, in his involvement with SETI, the search for extraterrestrial intelligence. He said, quote, "If aliens visit us, the outcome could be as bad as when Columbus landed in America, which didn't turn out well for the Native Americans. We only have to look at ourselves to see how intelligent life might develop into something we wouldn't want to meet." End quote. Some of these comments drew controversy, and a lot of them were taken out of context by the media and run with banner headlines like "Smartest man alive predicts that we're all doomed." I honestly don't know whether this kind of discourse is helpful or not. On the one hand, people are talking about it, on the other hand, they're saying things that are probably wrong. It's true that Hawking was a theoretical physicist, not an expert in AI or anything like that. But it's also true that he had a truly unique platform due to his fame and notoriety as a physicist. I can't get over the notion that with his passing, 10 times fewer adults can name a living scientist. That famous voice which he started to use in the 1980s was the voice of physics. Regardless of what he said, he spoke with authority, and people listened to him. That is an achievement in a world where anti-intellectual sentiment is on the rise. That is an achievement for a theoretical physicist. This show has mostly been about his scientific legacy, but the mere fact of his extraordinary life has been an inspiration to millions of people and challenged stereotypes about disability. There was a certain stoicism to how he approached the universe, and I use that term advisedly. He said, quote, "My expectations were reduced to 0 when I was 21. Everything since then has been a bonus." Marcus Aurelius, the Roman emperor and Stoic philosopher, told us to imagine that we had already died and experienced our allotted time, and then we should take the rest as a bonus and live it well. He arguably turned his disability into an advantage, becoming a uniquely iconic figure with perhaps one of the most famous voices on the planet. An artificial one that nevertheless spoke with great warmth and eloquence to the scientific community and to the general public. I really think that this is ultimately the essence of Stephen Hawking, especially later in his career. Face and voice of physics and science in general. He leaves behind an immense treasure trove of scientific research, but also writings and speaking eloquently about scientific issues, bringing his fascination with the universe to a huge number of people, many of whom would go on to study and make their own contributions. The number of people I've read in recent days who said that he was a big influence on them getting started in studying physics. And it's true for me as well. When I first read A Brief History of Time, I was amazed that I understood some of it, and I thought maybe this physics stuff might be something that I might want to pursue myself. And for me, if you love the subject, this should be the most important thing. There are people out there who are exposed to these ideas who never would have been without Stephen Hawking. In the long run, his greatest legacy is likely to be the generation of people he inspired to pursue physics, and his symbolism of this endless pursuit for fundamental truths about the universe in the face of great adversity. In this respect, he is truly irreplaceable. Amongst the many things he leaves us, there was a talk he gave by hologram at the Sydney Opera House back in 2015. You can hear the whole thing on the Ideas from the House podcast, An Evening with Stephen Hawking, and I strongly recommend that you go and listen to it because he discusses his life's work, the personal side and the physics side, in wonderful detail, and of course far more eloquently than I can. That voice will be missed in the modern world. So let's finish with it.
It has been a glorious time to be alive and doing research in theoretical physics. Our picture of the universe has changed a great deal in the last 50 years, and I'm happy if I have made a small contribution. The fact that we humans, who are ourselves mere collections of fundamental particles of nature, have been able to come this close to an understanding of the laws governing us and our universe is a great triumph. I want to share my excitement and enthusiasm about this quest. So remember to look up at the stars and not down at your feet. Try to make sense of what you see and wonder about what makes the universe exist. Be curious. And however difficult life may seem, there is always something you can do and succeed at. It matters that you don't just give up.